So that's what we'd have in each of these positions. So now in these areas of the box on our truth table, what we're going to end up doing is putting the ones, since we're trying to do a sum of products representation of our circuitry here based off of what we had a little bit earlier. We're going to put ones in these positions where they correspond to the ones from this original truth table. So again, we had a 1 in this position where we have A naught, B naught, C naught, a 1 here where we have A naught, B naught, C, and so on and so forth. All right. So given that that's the case, then we're going to create another truth table down here at the bottom, or pardon me, another Karnaugh map down here at the bottom. Okay, again, the Karnaugh map we have over here A and B. We need to use our gray code. So this is 0, 0. This is 0, 1. 0, 1. This is 1, 1. And this is 1, 0. This is 0. And this is 1. Okay. And remember, let's move this over here. Let's see if we can get both of these on the screen at the same time. Alright, we'll make this happen this way. So we have a 1 when they're all zeros. So that means we're going to put a 1 into this box right here. Okay. So what we're doing again is we're putting together the Karnaugh map, which will help us get a minimum number of terms and actual variables in order to represent the circuitry that was created by this truth table using the sum of products method, which gave us this really long equation. Okay, so we have, again, we have a 1 in this position. We have a 1 when we have 0, 0, 1. We have a 1 in this position here according to our information. Okay, and according to our truth table over there. We'll also have a 1 where we have 0, 1, 1. Okay, so 0, 1, 1, that would be in this position. We also have a 1 where we have 1, 0, 0. So 1, 0, 0, that's in this position. And we also have a 1 in this position. All right, so this is our Karnaugh map representation of what we have in the truth table over there. Okay. So now that we have our Karnaugh map put together, okay, with our outputs in the Karnaugh map, the next thing we want to do, all right, is we want to group our ones such that those ones is equal, the number of ones inside of a grouping should be equal to 2 raised to the x. Okay, it should be equal to 2 raised to the x. So that means it could be, let's say, and let's use an arrow. That means it could be 2 raised to the 0, 2 raised to the 1, or 2 raised to the 2 number of ones inside the boxes. Okay, but when we're grouping these, we want to group these based off of adjacent values, okay, or adjacent inputs. So, and what we mean by adjacent is when we look at the inputs, we can only have a 1-bit change between any of the inputs. So if we look between, let's say, these two values here, okay, in terms of our inputs, we have 0, 0, 0 representing this box and 0, 0, 1 representing this box. So there's clearly a 1-bit change. So these two would be considered to be adjacent. If we look at these two over here, what they end up having in common is they have 0, 0 between two of these, 0, 1, which is only 1-bit change between these two. And of course they have the same, oops, and I forgot C. They have the same value for C, which is both 1s. So these two are also adjacent. If we look down here at the bottom, we see that in terms of these two, they have in common that A is 1 for both of them, and B would end up being 0 for both of them. So then these two would be adjacent. But something else that's important to point out here is that these two ones up here are also adjacent to the ones that are down here in terms of them being only a 1-bit difference between the between their inputs also. Okay, So when we're looking at these Karnaugh maps, in terms of when we're trying to figure out what's adjacent to each other, the way to think about it is that what's up here at the top is also adjacent to what's down here at the bottom. Okay? So these two are actually adjacent to each other. And then what's at the left side here is also adjacent to the right side. So the best way to think about this is, let's say this is our Karnaugh map here. And I have to zoom out just a little bit. Bear with me. Oops. Alright, so this being our Karnaugh map here, so the way to think about it is, if we roll this now this way, what you'll notice is that they'll be adjacent again. Here will be adjacent to here, and here will be adjacent to here. And we can also roll it this way, where, and flip this over, these are also adjacent to each other. Okay? So in other words, whatever is in this box is adjacent to whatever is in this box, whatever is in this box is adjacent to whatever is in this box. And so we can, and again, they're also adjacent in this way. So if we take a look at the values on there, we'll see a 1-bit change between these two, we'll see a 1-bit change between these two, and we'll see a 1-bit change going across that way, and a 1-bit change going across this way. Okay? Alright, so now given that that's the case, again we can end up grouping now adjacent boxes to each other. So we have this one and this one that are adjacent to each other, and then they're also adjacent to the ones at the bottom. So together all of these four would be considered to be adjacent to each other, because this is adjacent to this, this is adjacent to this, this is adjacent to this, and so therefore they're all adjacent to each other. So that's one box there, and that box has 2 to the, let's see, there's 4, so that's 2 to the 2 ones inside of it. Alright, it has 2 to the 2 ones inside of that, so that leaves us then with the number of 4 ones being inside. And then also in terms of this one, and again we're trying to get the largest number of groupings here that we can possibly get. So we just don't want to circle this one by itself because it's right here next to this other one. So we also have a box that's right there. Okay, so we have those 4 together and these 2 together. So now in order to find our equation now for our Karnaugh map here, or pardon me, for our circuit, the minimum equation using the Karnaugh map, what we would do is we'll say, okay, what must be true about all the ones that are inside these boxes, okay, in each of the boxes. So let's start with the really big box first that has the 2 ones that are down here and also have the 2 ones that are up here, making a total of 4 ones inside that box. And what we can say about here, we see that in terms of the top and bottom, okay, the 1 here and the 1 in the A position and 0 in the A position, that means that they're different in these 2 rows. We have the 0 here and the 0 here for B, so that means B naught is common to all 4 ones that are in here. C, however, there isn't any commonality in there because this is 0 on this column and then there's 1 on this column. So that means then, in terms of just that box can be represented by just B naught. Okay, that box is represented by B naught. So that's one term. And then we use the plus sign now to indicate now that we're moving to our second box here. We're looking at what's common inside that second box. And if we look inside of this, or if we look at this box, we have ones in both of these two, right? Or ones in both of these 2 boxes, and they're grouped as a group right here. And what is common between the ones in these 2 boxes? Well, they have C, input of 1 for C being common between the 2 of them. And they also have an input of A naught being common for 2 of them. So that means that box can be represented by A naught C. And so what this is here, what this is saying now is that we can use Y being the output is equal to B naught plus A naught times C here in order to represent the same equation, okay, represent the same equation as what we had And let me grab this piece of paper here. The same equation as what we found using the sum of products representation here. Okay, the sum of products representation. These two equations will give us the exact same output. Okay, they will give us the exact same output. So therefore, then we can use this circuit here, or this Boolean expression here, or equation, in order to represent our circuit. And so our circuit then would end up being B, and then we'll knot that coming in here, so that'll be B naught. We'll take A, we'll knot that, and then we'll take C. We would AND A and C, so that's A naught that's going in there, right? We'll AND those together, and then we'll OR with B naught up here to then give us our output of Y. Okay, and so then that ends up being equal, or that ends up being the circuit realization for this equation, which is the same circuit realization for the truth table that we started out with over here on this previous page, where we needed the output when the input was all zeros. When we had an input of 0, 0, 1, we had a not as input, pardon me, an output. We had output of 1 for 0, 0, 0. We had an output of 1 for 0, 0, 1. We had an output of 1 for 0, 1, 1. We have an output of 1 for 1, 0, 0, and an output of 1 for 1, 0, 1. Okay. All right. So that concludes our discussion on truth tables, or pardon me, rather, Karnaugh maps. When it comes to trying to get the minimum realization for a given scenario or circuit that we need to set up based off of a truth table. And in there we also talked about gray code, which helped us to construct the Karnaugh map. Thank you very much for listening.